Recording, yeah. Hi, welcome to my talk on counterexamples in topology generated by large cardinals, and this is actually part one of a longer series of papers, results, talks, etc. on such constructions. And I'd like to remark that this is not exactly about counterexamples in topology per se. It's more about examples, properties, interesting results in topology, and how they react under large cardinals and behave under large cardinals. So generated here is sort of a misnomer, but the core basis of this paper is that some large cardinals create very interesting or odd properties in topology. Like, for example, I don't think this is true, but a super strong large cardinal can make it so that under it the real line is T3 or not even Hausdorff. Again, that's probably incorrect, but that's just a example. And as you can see, I have no formal university affiliation. So this is just a lone talk. This is not part of a larger seminar series, and I'm just doing this, I guess, all by myself. So first of all, we begin with the introduction and motivation of our paper and our talk, our definitions and appropriate machinery for this talk, and actually the rest of the paper that it was based off of. Counterexamples in topology generated by large cardinals, part 1, and is available on my website. Here, click mathematics papers, this link, and then here it is. But let's just read off of the slides first, and then maybe I might create another video explaining the paper in more detail. But this is just a general skim if or to get somebody interested in this field, because obviously mathematics is a social field. And then we go over trees and embeddings, which are a very important machinery that we use in this paper. And then obviously we go over counterexamples, examples, and just general elegant properties in topology. And the motivation for this paper and talk in general is to examine some further topological consequences of large cardinals. And for further in quotes, I'm actually not too certain of already in the books topological consequences of large cardinals. So I'm not exactly sure if there are other works like this out on, say, the archive, but I'm very sure that there aren't, because on the archive, when you search up the MSc code for topological counterexamples and the MSc code for large cardinals, nothing appears. So that's what we're assuming, that there probably isn't some vast literature on topological consequences of large cardinals, especially of topological properties and their interactions with large cardinals. I mean, of course, they can create stuff like cardinal embeddings, functions, and other elegant stuff like that. But with direct topological consequences, I'm sure that so this is why I believe that most of the results in my paper are quite novel. And also, forcings and forcing axioms already interact non-trivially with topological properties, particularly topological games. But technically, topological games don't really count as topological properties. For example, compactness is one, but topological games, one could say that's a structure in a very broad and vague sense, but not really a property per se. And there's actually a very good paper by Gilton and Holzhauser, I think that's how it's pronounced, which is essentially on strongly proper forcings and forcing axioms and their interactions with many topological games like the Menger and Rotberger games. And I haven't read that paper too much yet, but I guess it would be a good idea to read it. So that's why. Actually, yeah, that's an inspiration for our paper. Topological properties. So typically, whenever we talk about topological properties and structures and their interactions with set theory, we are usually talking about forcings and forcing axioms and whether or not these behave under say Cohen or Levy or cardinal collapse forcings. But we don't really talk about large cardinals per se. And I mean, there are already lots of non-trivial uses of large cardinals, especially measurable cardinals, weakly compact cardinals, strongly compact, and super compacts. And there's a few more, but measurables and the compact cardinals are what is usually used the most non-trivially in fields outside of logic. So I don't know off the top of my head, but there are applications of measurables in algebra, especially group theory, and also algebraic topology. And of course, there's just an air of elegance that is added when you're inspecting large cardinals and their topological consequences. And actually, I've read on the Athenoid Union, which is a Discord server for mathematics, by the way, conversation that rank interrank axioms, like for example I3, if it's supposed to be said that way, I3, that these large cardinal axioms, especially I3, are used even in finite constructions. So for example, a certain property that is finite or acts on finite sets might not be true under I3, and that's pretty expected of large cardinals. So yeah, large cardinals, pretty non-trivial properties, especially in topology and other fields, which is sort of the motivation and basis for our research topic. And we can also check up to which point strengths of axioms independent of Z of C do common topological properties break. And you could just remove the topological and it would make sense. And I suppose that one could do this for axioms. Like for example, if you have an axiom that is higher on the Levy hierarchy, you could check at which point in the Levy hierarchy do these topological properties break. But so far, we will just use large cardinals. I mean, yeah. And of course there's elegance. So here are the definitions. So a core definition that we use to work with topological properties or topological spaces on ranks of universes of ZF is of trees of ranks of universes of set theory. So for example, suppose that you have V sub 0, which is the base level of the universe, and then we can represent that, or yeah, I think represent would be a good term. I'm not sure if a good term that would express this term fully, but represent V this as the rank of V. So rank sub V sub 0 would just be 0. Yeah, one could just augment that as a function on yeah, function symbol on the relations functions, constant symbols on the model V. So in a way, one could think of the function R, which is titled the rank of a specific set in V, as an adjoining to the regular R, F, and C symbols of the model. And of course, we do this in terms of posets. And sorry for skipping slides, but that's an extremely important part of our construction. Otherwise, the other topological properties would not really make sense, especially in the scope of my paper. And note that this is not entirely new, and by not entirely new, I'm referring to the construction of ad hoc topologies on trees, not necessarily on universes of ZF, like models of ZF. But in 1977, Salah and Devlin defined topologies on trees before, but we focused chiefly on representing V in terms of trees and posets, and actually M2, which is a transitive model. And since it's transitive, we can simply just define an ad hoc rank and add that rank function to its relations functions and constant symbols. And of course, we cannot forget about Kunin's inconsistency theorem, which shows that an extremely strong, equal to, or stronger than an elementary embedding from the universe to itself is inconsistent with the axiom of choice, and displaces a hard cap on the large cardinal axioms we can play with and construct in terms of topology. So the reason is that the axiom of choice is extremely important for just adjoining ad hoc orderings and rank functions onto arbitrary transitive models of set theory. Without it, nothing would really make sense in the paper. Even if we don't use this tree and embedding construction, most of the theorems and proofs used in this paper rely on some form of the axiom of choice, so that's why we desperately need it. And the continuum hypothesis and other axioms like the countable chain condition, Martin's axiom, etc., they aren't really too relevant. So the core motivation for this tree and embedding construction is to answer, is the construction of the naturals from V preserved via the elementary embedding J into M. And this of course represents a measurable cardinal. So measurable cardinal, elementary embedding, critical point of a non-trivial elementary embedding from V into M, which essentially translates into is the construction of the natural numbers preserved under a large cardinal. And to that, answer is in the positive. And then from that, we can of course construct the real numbers in your typical undergrad analysis class-esque fashion. So if M, the arbitrary model that's also transitive, is not constructed via recursion, we can define an arbitrary p-order, which is a partial order, on M by assignment of arbitrary ranks, and we use the axiom of choice inside M of sets or classes inside M. And this is sort of self-explanatory. I don't think I have to do any sort of commentary on the slide. And we also give J in terms of an injection schemata between V and M. And this is done because acting directly on elementary embeddings, would require second order logic, which is quantifying over sets of sets, if I am remembering that correctly. So the reason why we give in terms of injection schemata is to avoid having to use second order logic. And this is also the motivation for Z of C's axiom of foundation being an axiom schema, because the full second order formulation, the full non-schematic formulation, would have to require second order logic, but since ZF is a first order theory, we have to use schemata, and this is the same, so we just use injection schemata. And injections preserve ranks of sets of models in that the order of the ranks and functions are preserved. And of course, one could argue, well, maybe non-trivially, via the regular definition of injection. So for example, if f of x sub 1 does not equal f of x sub 2, then x sub 1 is not equal to x sub 2, and we could apply that to ranks of sets of models. And also for counterexamples generated by large cardinals, one of its being homogeneity of spaces, which actually proved in the introduction. And also the stone-check compactification of the real numbers and topological spaces in general, Hausdorffness of the strong ultrafilter topology, and the either-or topology. And a space X is homogeneous if for any pair of points of the space X there is an auto-homeomorphism of the space mapping one point to the other. And this is the theorem that I proved in the introduction, and states if matcow B is an ultrafilter, then for a pair AB in matcow B, assuming low order, and if B is a subset of matcow B, then given B is solely comprised of pairs AB, an element of matcow B, and is also a filter, then B is also homogeneous, and B can also be of any cardinality. And actually, here's a major typesetting error or typo. This is supposed to be uppercase. And the proof sketch is that we set matcow B to be an ultrafilter generated or in part by a measurable, using, well, the formulation of measurable cardinals using ultrafilters, and using ultrapowers. I'm not sure how to pronounce that. We saw that respect to matcow B, one can be similarize the factors of the ultrapower. And of course, this part might seem hand waved, but in reality, it's more, how do I say this? Squishing of the factors. No, not squishing. No restricting the factors of the ultrapower with respect to matcow B. And in my original paper, so this is a misstep. Theorem 1 was originally false under measurables, but it is actually only false under large cardinals stronger than Vopenka's principle. And here's another relevant theorem regarding homogeneity of spaces, which essentially states that if X is a zero-dimensional space that is first countable, then X omega, I think it's supposed to be countable. Yeah, I think you're just supposed to pronounce that first countable. I'm not sure what Steen and Seeback were originally going for when they chose that notation, but let's assume that it's just countable or first countable is not homogeneous for Vopenka's principle. And the proof of this essentially goes as the proof of inconsistency. Well, not really inconsistency, but counterexamples generated from Vogt-Panca's principle in my original paper. Vogt-Panca's principle seems very strong in regards to topological properties in that regard. So under a measurable cardinal, the stone-check compactification of the real line is preserved in that it is still possible under the embedding J from V to M with n transitive and kappa the critical point of J. And as a lemma or corollary, for any compactification of the real line, it is preserved under a measurable cardinal. And as a theorem, the stone-check compactification of the real line is preserved under a large cardinal weaker than the least large cardinal that is inconsistent with set of C. Now, it's even preserved under Vogt-Panca's principle, and actually, even if the rank-into-rank axioms were consistent with set of C, this stone-check compactification of the real line would still be preserved. So it's only really the axiom of choice limiting us here. If the axiom of choice were not taken into account, one could go indefinitely higher and higher and higher in the large cardinal hierarchy, and this probably wouldn't budge. One might have to wait until Reinhardt or a straight up inconsistency for this not to be preserved. And in Steen and Seebeck's counterexamples in general topology, which is, by the way, where I get most of these counterexamples from, Z sub n is not Hausdorff under Vogt-Panca's principle, under the strong ultrafilter topology. So it's essentially the positive integers under the strong ultrafilter topology, and it's not Hausdorff under Vogt-Panca's. And here is sort of an ad hoc topology, which was made by Steen and Seebeck, which is the either-or topology is a topology defined on the closed interval x equaling closed interval formed by -1 and 1 by declaring a set open if it either does not contain the set containing 0 or does contain the open interval formed by -1 and 1. And these are some 5 properties that result from the either-or topology defined on the closed interval x, and 1, 2, 3, and 4 are all not preserved under Vogt-Panca's principle. And it seems like 5 is pretty special in that it is preserved under Vogt-Panca's principle, and in the same way that the stone-check compactification of the real line is preserved under indefinitely, well, not really indefinitely, but Vogt-Panca's principle, one could presume that non-regularity of a topological space is one of those topological properties that continues to be preserved even under extraordinarily and stronger large cardinal axioms. So, natural question to ask is, what distinguishes these properties, like the stone-check compactification and these properties down here, that make it so they are preserved under, well, not preserved under Vogt-Panca, but this is. And actually, when I was taking a shower, I thought to myself, maybe it has to do something with the Levy hierarchy or something similar of these formulae. And I guess I might speculate that in part 2 of my paper or talk. And I'd like to wrap up in saying that this talk and paper it was based off of is very limited, only showing 4 examples and major theorems. In order to reveal the structure of these large cardinal and topological property interactions, many more examples are needed. And this is exactly why this paper and talk is titled Part 1, because this is only an extremely brief introduction to the many properties of topological properties and large cardinals, and also the interaction between set theory and topological properties in general. And I wonder, probably it's not going to be the same, but akin to the finite group classification project in group theory, I wonder if this project or something along the lines of that could lead to a similar project, like classifying the finite groups, but only that, but replaced with topological properties holding for certain large cardinal axioms or even types or strengths of axioms. So that's just my 2 cents there as a potential implication of this project. And of course, thank you guys for listening. I really want to end off on a cringy note saying thank you all for watching. Please hit like and subscribe. As this is being presented to mathematicians and probably will be in the future, I'll just keep it formal. I mean, it's kind of interesting that at a young age, like I'm 14, and at such a young age, I'm doing this type of stuff instead of, like, you know, playing Fortnite or some stuff like that. So, bye.